Yes, Samakula. Kenneth. Hello, Kenneth. Kenneth. Hello. Samakula, are you able to hear me?
Yes, doctor.
Okay. For you don't have a lecture today?
I'm free.
You're free.
Yeah.
Okay. Sometimes it is important to record when there is someone hearing so that they can. Are you able to see my screen?
Yes, doctor.
Can view the screen.
Yes, doctor.
I was at this point before getting off, and I had highlighted that this is the probability function, the derivative of the probability function for a pure depth process. And this derivative, this equation A, can be solved as before, the way we solved equation. And so this is a critical equation to generate if you are to solve either recursively or using the probability generating technique. If I can take you ahead, there is another huge one where you combine birth and death. And it can even be made extremely huge if you bring in other vital dynamics like migration. So sometimes when it becomes huge, it becomes mathematically intractable. And so now solving this equation, so I'm saying I'm highlighting the recursive solution is possible, but we are going to solve it using a probability generating function. And the probability generating function for this is as before. We defined a similar generating function. That generating function is there for you to use. By definition, this is a recommended, a preferred generating function because once you define it in that form, it's very easy to satisfy all the nice properties of the generating function. All right. So define the generating function for the probability distribution of P of N. So this defines, or I'm saying that it is define a probability function for the probabilities, for the probability distribution of P of the probability function Pn of T. And so as before, we take the derivative, that's the partial derivative with respect to T is that, and that gives us equation B. I don't have to explain this any further because I've just explained it in the previous pure birth process. And so we can now put A, we are putting equation A into B. And with simplification, when you substitute A into B, we are substituting for only the derivative of the probability. And simplifying, all what I'm trying to do here is a simplification. So I'm trying to simplify. And so the simplification can be done as before. The simplification can be done as before. So I have, if I can explain this, this is the summation x power n. Pn plus 1 minus that guy. But when you check here, mu is a constant. And so we seek to factor to filter out the constant mu. Mu is a constant, so it can be taken out of the summation sign. And so we are summing n plus 1, x power n, and so on. Now from here, what I'm trying to highlight here is in there, we have the partial derivative with, if you can note here, that the partial derivative So the partial derivative with respect to x, h. What did I pick? Let me pick my pencil. So the partial derivative with respect to x of x power n. So note that the partial derivative with respect to x of x power n plus 1 is equal to n plus 1 x power n. That's the partial derivative of x power n plus 1 with respect to x. And you may also wish to know that the partial derivative with respect to the partial derivative with respect to x of x power n. Of course, we could even talk in terms of full derivative, but because there is another variable, then we can't do that. So that is n x power n minus 1. That's what I was trying to highlight here. So if you can note here, you just
Yes.
derivative. More people have joined with notes, with noise. Oh, Awero, you seek my admission? Okay, allow all. Mutebi John, Awero Wilfred, are you the one making noise? Okay, let me force myself to mute you. Okay, I was explaining this, I'm explaining this term. So what you have to note is that the partial derivative x power n plus 1 is n plus 1 x power n. Okay? And the derivative, partial derivative x power n is n x power n minus 1. So meaning that we have to do something about this term. Something has to be done about that term, right? And so if we are to do something about that term, to introduce, because this is okay, I don't have any problem, but here we have issues because I have n x power n. So to introduce x power n minus 1 here, we introduce an x, but that x shouldn't contradict the existing mathematics. And so how do we introduce that x? So pay attention here. So that x is introduced by factoring an x, because in principle, x times x power n minus 1 is x power n. But the advantage here, once you introduce that, then you have the derivative, the partial derivative of x power n as x power n minus 1. So try to take note of that one, that introduced quantity to cater for the partial derivative. Hope that is understood. Otherwise, if you are not careful, you are going to complain about the introduced x power n minus 1. Is to cater for the partial derivative, the derivatives. All right, after noting that, then we have this term after taking note of those computations, then you can take note of the following. So what I've tampered with is that term. And so with this, it means that in here, this guy is the derivative. So if you take a derivative of this, especially the derivative of x power n is n x power n minus 1 times the probability. And this quantity here is the partial derivative. So this is the derivative of that. And here we have the derivative catered for. And as I explained before, the derivative operator is linear over addition. So you are now free to either factor the derivative operator outside or maintain it inside. But advantageous to take it outside. So here we have the partial derivative function taken outside, and this is the partial derivative. Once you do that, then you can clearly see that you this guy is by definition the generating function, and by definition this is also g of x. So it doesn't matter the value of n, but so long as you have x power n probability at any time t being n, the population being n at any time t, then that's a generating function. And so from that generating function, all these I've explained before in the pure birth process. So from that generating function, so this is partial derivative of g with respect to t is equal to that guy. And so we can now write the generating function. So the partial derivative of g with respect to therefore is mu, partial derivative of g with respect to, so this is not t. So try to take, there are some mistakes I have. So this is x. So you can always, if you see something inconsistent, you can always rectify it. So that is x. Let me try to rectify it on my original copy. I can find it quickly. So this is respect x. So the partial derivative with respect x is equal to that minus mu x partial derivative of g respect x. And so we get a partial differential equation. So such a partial differential equation, of course, better to maintain it in the form I'm highlighting as C after factoring this partial respect to x. So once you have it in this form, then we can solve. And I said this equation is always solvable by the method of characteristics or the auxiliary equation. So that method generates for us what we call characteristic equations or auxiliary equations. And so these are the auxiliary. I said, if you want to see it better, the better way of looking at it is by looking at this as 1 over the partial derivative with respect to plus a mu x minus 1. That's the step I'm not writing for you. Times the partial derivative with respect to is equal to 0 over partial respect to g. And so from that, you take the reciprocals and write full derivatives to generate the characteristic equations. So the characteristic equations therefore are as given above. So given those characteristic equations, then we can solve. We can solve the various pairs as I mentioned them. So there are 3 possible pairs, but you find, I don't want to limit your curiosity. You can always bring in the 3rd one and see how far you are going to go. But solve the first pair, and that pair is, you are going to discover, I don't want you to take it as gospel truth. It is always solvable by separation of variables. So the variables here are separable, and so separate the variables and see that you get direct functions unlike in the pure birth process, under the pure death, you don't have even to go into the partial fractions. And so when you separate the variables, you integrate straight away to get mu of t plus a constant is equal to natural log of x minus. So it doesn't matter which direction you throw the constant of integration. Now rearranging gives me x minus 1 is equal to C1 exponent of mu t. This constant is no longer of the same value as C1. Try to take 4 out. Therefore, the constant C1 is x1 minus exponent of negative mu t. And so this is the first constant C1. You may wish to highlight it. So you can highlight this constant as say equation 1. Then the other auxiliary pair can be generated from these two, simpler. If you compare these two, you'll have a solution. The solution is always there. So from the other pair, which is also simple, as you can see, you get the integral with respect to g is equal to the integral of 0 with respect to t. And so g of xt is equal to the constant c2. But as I noted, that constant c2 is always a function of the first constant. In any case, you can see that the first constant depends on x and t. The first constant is always a function of x and t. And this is a generating function depending on x and t. Therefore, natural to note that C2, which is a constant, is a function of another constant. Therefore, g of xt is equal to mu, rather psi of C1, which C1 is as defined in the other equation I highlighted. Then we begin. The battle is just beginning. So what we do now? We introduce the initial condition. I explained this initial condition before. The value of the generating function at t, initially at t equals 0 is x power, the initial population, because the probability of the population being taking on an initial value is 0, rather is 1. So if that's the initial condition, then we note that g of x0 is equal to psi of, so when you put in this equation, you can now in this equation put a t of 0. So when we introduce t of 0, it means g of x0 is equal to psi x minus 1. And that is equal to x power n naught, the initial condition. Of course, I'm just doing a reflection of what has already happened in the previous case. And so we note as before, I say that it is not a good way of defining a function in this form. The function must admit one input. I don't have to put x minus 1. I need an x, a single variable. And so if we let theta to be x minus 1, this shows that x is theta plus 1. And so psi of theta should be some introducing theta in this statement. So psi of theta should therefore be equivalent to theta plus 1 power n naught. So what do we see now? We have our theta. What is theta? No. Psi of theta is equal to theta plus 1 power n naught. And so if we get back to this statement, remember this statement is the one giving us a generating function. We can now have an input here. So if we have this input as our value of theta, we therefore know that f psi of x minus 1, x exponential of negative mu t, and this without loss of generator, this is our generating function g of xt from above. If you are observant, this is our generating function. G of xt is f psi of x minus 1 exponential of negative mu t. And so when I write that, then I'm here. But because of this, if this is my input, according to that, then I have the input plus 1 raised to n naught. Are we together? Mutebi John.
Yes.
Are you following that?
Yes, Doctor.
You're following. Wonderful.
Yes, Doctor.
Okay. So you are going to continue in that direction. So what have I obtained now? I've obtained f psi of is equal to that. And what I have at hand is my generating function. Because from before, as we're solving the partial differential equations using the characteristic approach, this g of x was obtained as f psi of x minus. I requested you to read it further. Because here I'm not teaching a full course of PDEs, but I'm teaching you a course of biomathematics. And so you can get to a full course of PDE and read, or if you on your computer, Google the method of characteristics while solving partial differential equation, you always get something. So therefore, I have the generating function. So I can even do the clapping and shouting. I've got it, right? So what I have here is the generating function for a simple, pure death process. That's the generating function for a simple, pure death process. What do we do with that generating function? So we can do a lot, but among the things we wish to talk about here is, are we able to find the expected population using that generating function? Are we able to get the expected population? Use the definition. The expected population is the expected population is the derivative is obtained from these partial derivatives. This is one. So you can either take the partial derivative of the natural logarithm of g at x equals 1, or the direct partial derivative of g with respect to x at x equals 1. That gives me the expected population. And so what does this generate? Get to this, of course, differentiating it, having taken natural log is better. Logarithmic differentiation at high school, you did it. And so we can benefit from that by taking the natural logarithm of both sides and respecting the rules of logarithms. We get here, right? And so, and there are various ways of writing this statement. I don't want to limit you. You can remove the brackets and do all that you want. Otherwise, natural log of is equal to n naught natural log of that quantity. Then the partial derivative with respect to x is First of all, the partial derivative is you take the derivative, this is a constant, n naught, the derivative respect x of this guy. This is the only term depending on x is exponential negative mu t over the function. And so computing this at x equals 1 generates for us, when you put x equals 1, this guy goes to, this term gets to 0, clearly. And so the remaining terms reduce to this guy. And this expectation of n of t is n naught exponent of mu t. I'm highlighting that for you. Otherwise, that expression, as I've kept reminding you, should remind us that expression. We should be able to remember the following from the deterministic approach. So we're going to find that these two approaches, the stochastic and deterministic, somewhere they agree, but the stochastic is recommended if you are modeling a population within a short time where activities take place in the shortest time possible. So for instance, if you recall from the derivative, from the deterministic approach, using a Malthusian model, mu n, and this is negative, not so? Negative mu n to signify death. So this is negative mu n. If that's the model, this subject to an initial condition, suppose n naught is the initial population, then n of t, the solution, is n naught exponent of negative mu t. And this solution we have is the expected population. On average, the population is expected to take on that value at any time t. And this doesn't contradict. Now, you are going to find that under stochastic process, if there are so many quantities to model, then this one brings you probably closer to the realistic values of the population. Hope that is noted. And that was also true for a pure birth process. Now, let's continue with other quantities. The variance is also another quantity to be computed. And by definition, this is the variance. You see, if something is a definition, it means you can use it for free. But sometimes you may wish to see the details, the nitty-gritties, why that kind of definition was put. That's not a problem. All right? And so, using this definition, the second partial derivative of natural log of g at x equals 1 plus, this is what we have as the expected value. In fact, the variance, the usual way of computing the variance, if you can remind me, how do you compute, for instance, for a random variable, var of x is always e of x squared. This should also remind you about this. Is it e of x squared minus e of x? But for the random variables, you take the mean squared, you know so? E of x squared minus e of x squared. Is that the definition?
Yeah.
Yes. Otherwise, it is e of x, expectation of x squared minus the mean, which you normally call mu squared. And so you may, when you look at this statement, it is almost taking you there. Of course, with some different, because here we are talking about derivatives. So it is reminiscent of the variance of the random variable. So using this definition, then the variance can be computed. So you can now, this partial derivative is with us. We don't have to take it again. It is as computed while computing the expectation, right? So I don't expect it to change. That is n naught exponential. Then from, of course, I'm highlighting it here so that you know that you are taking the second partial derivative from that partial derivative. So when you take the second partial derivative from here using the quotient rule, you know what the quotient rule is. This is it the u, v, the u, the x. So my v is a constant. I'm about to get off, but don't worry. There's a warning. Have you received it? My u is a constant and v is the variable. So everything gets to 0. Then minus u, which is that. Then the partial derivative of v respect to. And this partial derivative is a negative. Is it a negative? Or no, it's a negative. Hope I'm not violating the mathematics. It is v du dx minus u dv dx. Oh, my dv dx is a positive. All right, so it's okay. Then over v squared, and this is here I'm squaring the denominator. Right? Now simplifying this at x equals 1. I've already introduced x equals 1, so this goes to 0. In other words, I mean with that gap. And so this is the second partial derivative of natural logarithm of the generating function with respect to x at x equals 1. Now from where the variance can be computed as this guy plus the mean. And so, which reduces to that. Of course, try to simplify and get there. Otherwise, this quantity I have here is the variance of the population. So the statisticians will tell you what the variance measures. All right. So that is the variance of the population. Now I had an assignment I wanted to give. So you are going to allow me end here. Given the second warning, I'll continue with my recordings during another lecture. And so allow me to end here. I'm going to organize these recordings and upload them on Mwere. Then I'll continue from exactly this point. But I wanted to give an assignment. Should I put that assignment on Mwere?
Yes, doctor.
I'm going to put that assignment onto Mwere to help you work through before my next lecture. Let me try to upload that assignment on Mwere. That assignment you should be able to work on the pure birth and death process yourself. So that will give me the expression you're going to generate. Let me write that assignment. I'm going to upload it for you onto Mwere. So wait for it. And let me also ensure that all these audios are uploaded onto Mwere. So let me not open another session. I know this one is remaining here. I have some 5 more minutes. I wish to end at this so that I also take a break. So bye-bye now. So let me this link.
Thank you.
This link, we should be able to use this link next time. so that, but if we are unable, I'll send another one. Right? Okay, keep well for now. Any question?
Doctor,
Yes, please.
you told us that you are going to summarize for us these notes here. Are we going to phone them or Mwele or Mint?
All these I'm using that are in my, that are handwritten. I'm just summarizing them from
Yes.
notes I sent. I'm just expanding a few things and trying to explain a few details so that you are able to follow. So I'm going to upload all this stuff onto Mwele. I think I should do it in the next few minutes. All right?
Doctor.
Okay.
Day.
Yes. I don't know.